In this video, we're going to learn how to solve an exponential equation using logs instead of our graphing calculator. Our steps are very similar to when we solved a log equation, except this time we're going to be doing some things backwards, or the inverse direction. This equation looks pretty familiar. It looks like one of our decay equations. Our first step is going to be to isolate the base and the exponent. So the base in this situation here would be this set of parentheses, and the exponent would be x. So we want to have just those two things on that side of the equation before we go on to that next step. So let's get rid of this 700 with some division. We'll divide both sides by 700. That's going to leave me with this 1 minus 0.65 as our base, x in the exponent, and I'm going to simplify this 400 divided by 700 to 4 over 7. I'm also going to simplify inside our parentheses here. Really, we could just call it a 0.35. And now we have just the base and the exponent, so step 1 is done. Now we're ready to change forms. What we're going to be doing, though, is going from exponential form to log form. I'm also going to show you another method of doing this problem, but I do prefer the changing form method just because it's it's more consistent with what we were doing with our log equations. Okay, so we're going to change forms. Our base of the log is going to be 0.35, since that's the base of our exponent. Our argument is going to be the 4/7, and logs equal exponents, so this one's going to equal x. And look at that. We've changed forms, and our last step is to solve for x, but we already have x by itself. So we are actually done with this problem. We have exactly what x equals. This would be an exact answer. If we wanted to, we could type this in the calculator to get the approximate solution. All right, so one other way, let me just label this. This was the changing forms method. The other way is to use log as a verb. I want to log both sides of the equation. Oops. And that might actually make some more sense because we're typically doing the same operation to both sides to keep that equality. So to do this, we really are just going to make each of these sides the argument of a log. Right? If these two things were equal to begin with, if I take the log of them, they're still going to be equal. But I also get to choose my base. So I'm going to choose a base that makes sense. I would love for this x to be by itself eventually. Maybe there's a way we could do that right now. We can choose a base so that the answer to this would be x, and that is the same base as the argument's base. So when I make these match, I know that this simplifies to the exponent. That would just be x. And you'll notice now that both of these methods, oops, make sure we do the same base on both of those. Both of these methods have the exact same answer. It's just how you want to think about them. All right, let's try another problem. Here we have a pretty complex exponential equation just because there's a lot of steps here. We're going to have to undo things. But it all comes down to these basics. We want to isolate that base and the exponent. Here, we have a 3x minus 2 as the exponent, and the base is just the 2. So those are the two things that we want to keep on the left side. We want to get rid of this plus 4 and get rid of this 9. So let's get rid of this 4, subtract 4 on both sides. And now the 9 is being multiplied with the 2, so we're going to undo that with some division. So now we have a base with an exponent, all isolated by itself. So step 1's done. Now we're ready to change forms. And you could also do the other method of logging both sides. Either one's fine. I'm gonna continue here with the changing form. So this is gonna turn into log base 2 of 7/9 equals the exponent 3x minus 2. I've changed forms. Lastly, I'm gonna solve for x. So to get x by itself here, we'll start by adding 2 to both sides. This 2 cannot be added to the argument of the log. So we're just going to tack it on to the end here. And then we're going to divide both sides by 3. This is also something we can't really simplify right now. So we're going to have this fraction as our answer. So we have log base 2 of 7/9 plus 2 divided by 3 as our exact answer. And if we wanted the approximate answer, we would type that in the calculator and make sure we round to anything we're being asked to round to. All right, one more example. So this formula that you see here is called Newton's law of cooling. So basically, if we have an object with whatever temperature it has, we leave it in a room that is colder than that object, the heat is going to dissipate, and it will take a certain amount of time to get down to a certain temperature. So we have lots of different variables in this equation, and we have lots of numbers to plug in for those. So let's read through this and see if we can kind of sort this out. After heating up a teapot, a cup of water is poured at a temperature of 203 degrees. So this object is going to be hot water. Its starting temperature or initial temperature is 203 degrees. So let's find initial temperature in our list here. So initial temperature, that's going to be T sub 0. The cup sits to cool in a room at a temperature of 72 degrees Fahrenheit. Okay, so 72 degrees is the temperature of the room. That's the temperature surrounding the object. We're going to call that T sub A. And then this cup of water reaches the temperature, it's cooling off, of 191 degrees Fahrenheit after 2.5 minutes. So this is the new temperature after a certain amount of time. So if you read this, this is T, temperature of object after time. And here is our time, 2.5 minutes. That's lowercase t. So I've counted up, let's see, 4 things here we could plug in, but we have 5 variables. Notice that the question's asking us to determine that last one. We need to figure out what k is, which is called the decay constant. So we're gonna plug these numbers in, and we're gonna have to solve for k. Notice that T sub A is actually something you plug in twice. All right, so let's do that. I'm gonna write that on the next slide. That is what we get when everything has been plugged in appropriately. And we still have our steps on the side here to remind us. Our goal to start things off is to get the base and the exponent all by itself. Where is that exponent? That's over here. This negative k times 2.5. What's the base of that exponent? That's the e. Everything else over here, that's got to go. So let's start by getting rid of this negative, or subtracting 72 here. So I'm just doing that on my calculator. We get 119. We should also simplify inside these parentheses here. That becomes 131. And we still have e to the negative k times 2.5. All right, we are still not done with step 1. This 131's got to go. So let's divide both sides by that. And notice that here we have a division problem. We're not going to actually type that in our calculator. we're going to save everything to the very end here. If we have to round, we'll do it one time. Okay, now we've finished step 1. Here's our base, here's our exponent. I'm going to change forms next. Ooh, our base is e. That means I'm going to use ln. Remember, that's a log with base e. Our argument is going to be the 119 over 131, and that equals our exponent. All right, let's clean this up, right? Negative k times 2.5, isn't that really negative 2.5 times k? We don't want the negative 2.5 there, so let's divide both sides by that negative 2.5. Once we do that, then we'd have k by itself. So it looks like we have log of 119, or ln of 119 over 131 divided by negative 2.5 as our exact answer. If we want the approximation, type it in the calculator. All right. Have fun solving your exponential equations.